Let's start our next section. So we're going to start section 14.1, which is about iterated integrals and area in the plane. So let's look at an integral, and it's one kind of similar to one I think we've seen previously. Let's evaluate the integral from 1 to x, 2xy plus 3y squared dy. So we saw these kind of integrals back when we were in the partial derivatives section. So notice what variable you have here. What's my variable for my integration? It's y. So then you're going to treat x like it's a constant and compute this integral. So the integral from 1 to x will be, well, you're going to have, it'll be xy squared plus y cubed. Again, your only variable is y. And now in place of y, you're going to replace y with x and 1. So here, you're going to get, if I plug in x, it'll be x cubed. So I'll just use parentheses. It'll be x cubed plus x cubed minus, plug in 1, x plus 1. So I'm going to get 2x cubed minus x plus 1. Now notice that the only variable I have is x. I no longer have the variable y. All right, so let's take this another step further now and look at the following example. So let's evaluate the integral from 1 to 2, the integral from 1 to x, 2xy plus 3y squared dy dx. Now notice the integral inside of this bracket. This was the same integral that we just computed from the previous problem. So this one is from the last problem. We already computed that and we got this answer right here, 2x cubed minus x plus 1. So what I can do is now plug in that. So now I'm computing the integral from 1 to 2. It was 2x cubed minus x plus 1 dx. Well, this is just our normal integral. We do the reverse power rule, x to the 4th over 2 minus x squared over 2 minus, or plus x. No, that should have been a minus 1. Here, there's a minus 1. I didn't distribute the minus that I should have distributed back here, so let me fix that. That should be a minus 1. So minus 1 from 1 to 2. So plug in 2. So 2 to the 4th will be 16 over 2. It's 8. Minus 2 minus 2. Subtract, plugging in 1. 1/2 minus 1/2 minus 1. The 1/2 and the minus 1/2 cancel here. So you're getting 4 plus 1, or 5. Now, I will say that this integral in this last example, this integral is an example of what's called an iterated integral. And I want to note that usually the brackets won't be written in there. So if you go back to the last example, there were brackets at the beginning. Usually those won't be there. So iterated integrals kind of have this format where you're integrating some function, dy dx. So from a to b, g1x, g2x. So those bounds are functions of x, which is what we saw in our last one. Or you might see something that looks like, say, or the integral of, again, some function xy dx dy. And now your bounds will go from c to d. And then these will be functions of y now, h1y, h2y. So I do want to make one kind of note here is that these outer bounds here must be constant. So I'll say the outside limits must be constant. But then these inner limits here, these are allowed to be functions. They don't have to be constants. And so I want to say that these bounds of integration determine what we're going to call the region of integration. So let's look back. For example, let's say we're looking at that integral 1 to 2, 1 to x of 2xy plus 3y squared. So these outer limits here, these were my bounds on x, so x goes between, so here my variable is x for this outer one, and so x goes between 1 and 2, and then these inner bounds are for the variable y. Y goes between 1 and x. So let's see what region does this correspond to in the xy plane. If I replace that last inequality with an equals, y equals x, that's a line through the origin. Okay, so I'm told x goes between 1 and 2, so I'm looking in between here, and y, the smallest y is 1, so I'll graph y equals 1 here. So my region is going to be this triangular region right there. So that would be my region of integration for this particular example.